rates of reaction. We all get speed, right? A car going at 70 miles per hour, an athlete running the 100 meters. But how do you measure the speed of something happening in a flask? It's not about distance over time, but that core idea of change over time is exactly the same.
What on earth is rate of reaction? You're going to hear that phrase a lot, so let's make sure we know exactly what it means.
At its heart, it's really simple. The rate of reaction is just how fast your starting chemicals, your reactants, get used up. Or, looking at it another way, how fast your new chemicals, the products, get made. It's just the amount of stuff that changes over a certain amount of time. That's it.
So, why do some reactions happen in a flash, while others, like rusting, can take years? Well, the answer to pretty much everything in this topic comes down to one brilliant idea: collision theory. Get your head around this, and everything else will just click into place. For any reaction to happen, two things have to occur. One, the particles have to physically bump into each other. Two, they have to smash into each other with enough energy to actually do something. Think of it like a high five. A little tap is no good. You need a certain amount of oomph for it to count. We call this minimum energy the activation energy. So when we change things like temperature or concentration, all we're really doing is finding ways to make more of these successful, high-energy collisions happen more often.
Okay, so that's the theory done. Now let's get practical. How are you actually going to measure reaction rates in the classroom?
So, one of the classic experiments is the disappearing cross. You mix two clear liquids, and they react to make tiny particles of solid sulfur. This makes the whole mixture go cloudy. All you do is put the flask on a piece of paper with a cross drawn on it and time how long it takes for that cross to vanish. Simple. The faster it disappears, the faster the reaction.
Another brilliant way to do it is to collect any gas that's being produced. You can use a gas syringe where a plunger gets pushed out as the gas fills it up. Or you can bubble the gas into a measuring cylinder that's upside down in a trough of water. Now the key here isn't just to time the end of the reaction, but to record how much gas you've collected at regular intervals, say every 30 seconds.
And a third common method is to measure the loss in mass. If your reaction makes a gas, like carbon dioxide, you can just do the whole thing in a flask sitting on a digital balance. As the gas escapes into the air, the mass on the balance will go down. You just record the mass at regular intervals. Oh, and the cotton wool? That's a classic exam question. It's there to let the gas out, but it stops any acid from splashing out, which would totally mess up your results.
Because a good graph doesn't just show you what happened, it tells you the whole story of your reaction.
It doesn't matter if you are measuring gas volume or mass loss. Your graph is going to have time along the bottom and the amount of stuff you made up the side. And pretty much every single time, you're going to get this classic curve shape.
The number one key to reading these graphs is the gradient, the steepness of the line. Where the curve is steepest, that's where the reaction is going like the clappers. As the curve gets less steep, the reaction is slowing down. And when the line is totally flat, the reaction's over, finished.
And this is where it all links back to collision theory. Right at the beginning, you've got loads of reactant particles, so they're colliding all the time. That's your steep gradient. But as they react, they get used up. There are fewer of them around, so they don't collide as often, and the reaction slows down. That's the curve getting flatter. And finally, when one of the reactants is completely gone, the collisions stop, and so does the reaction. The line goes flat.
Okay, let's pull all this together and focus on the main event, turning all this knowledge into marks on your exam paper.
In any question about these experiments, you've got to talk about control variables. It's all about a fair test. If you're investigating how concentration affects the rate, you can only change the concentration. Everything else, the temperature, the surface area, you name it, has to stay exactly the same. Otherwise, you've got no idea what's actually causing the change you're seeing.
Here's a little tip. Examiners love safety questions. So for any of these practicals, the first thing you should say is, wear eye protection. Always. Then mention the specific hazards. For the disappearing cross, you need to know that it can make a little bit of toxic sulfur dioxide gas. So doing it in a well-ventilated room is a really important safety point to make.
You are almost guaranteed to get a 6-mark question that looks something like this, and the answer always comes back to collision theory. For this one, your thought process should be higher concentration means more acid particles in the same amount of space. That means they're going to collide with the magnesium more often. More frequent collisions means more successful collisions per second, and that means a faster reaction rate. It's a chain of logic, and it works every time.
So let's boil it all down to the 3 absolute essentials you need for your revision.
Okay, here it is. Number 1, the definition. Rate is just how much stuff changes divided by time. Number 2, the theory. Collision theory is your why. It's all about how often particles successfully collide. And number 3, the graph. The gradient tells you everything. Steep is fast, shallow is slow, and flat means it's all over.
And I'll just leave you with a final thought to chew on. We know how different things can speed up a reaction, but how could you combine them? If doubling the concentration makes it twice as fast, what happens if you double the concentration and increase the temperature? How do these effects stack up? Now that is when you really start thinking like a chemist.